Okay. We looked at the mathematical electron at the Planck level. Here we put our electron inside a 4-axis hypersphere. This hypersphere is expanding 1 Planck unit at a time, and so we can measure the expansion in units of Planck time. The velocity of expansion correlates to the speed of light. This means that a particle that is motionless in 3D space is traveling at the speed of light in hypersphere coordinates. Relativity then becomes the mathematics of perspective when translating from the hypersphere and 3D space coordinate systems. Instead of a wave-particle duality, at the Planck level, our particles will oscillate between an electric wave state and a mass point state. The mass point state has fixed coordinates in the hypersphere, but it occupies only 1 unit of Planck time. In this diagram, the point states are represented by those dots. And so here we have 2 particles with a frequency of 6. This means that every 6th unit of Planck time they are mass points, and so they have coordinates in this hypersphere system. A is stationary in 3D space, B is traveling near the speed of light, actually 0.866 c, and so after 1 second B will have traveled 260,000 kilometers from A in 3D space. When seen from the A timeline, B will reach the mass point state after 3 units of Planck time, after 3 TP, and so we'll have twice the mass of A relative to A. Both A and B started at origin O, and as the hypersphere expands radially, both A and B will have traveled the same distance in hypersphere coordinates, OA equals OB. And so B can argue that it is A that is moving away from B. As each step requires 1 unit of Planck time, B can never attain speed c, although the smaller the particle, the faster it can travel. And so, at this point, this is the maximum velocity of B that B can reach, and it is 1 Planck. It is Planck mass, but of course, velocity c is the exact horizontal line. In this diagram, we start with B at origin O, and here t equals 1, arbitrary time t, and B is in the wave state. As the universe expands, it pulls B along with it, and the wave state expands correspondingly. At t equals 6, the particle B collapses back into the point state. And so, and then we find that this point state then becomes the new origin O. The universe continues to expand to the wave state collapse back into the point state, again a new origin O, and so on, ad infinitum, or to the end of the universe. And so particles do not have any inherent motion of their own. They are pulled along by the expansion of the universe itself. Without this expansion, there would be no motion within the hypersphere. Now, the wave state expands radially, and so how does the particle know where the point state will occur? And for this we give the particle a north-south axis. And so although expanding in wave state throughout this diagram, the point state will collapse in the direction on the axis of this north-south spin axis. And so this means that, for example, if I want to change the direction of A, the direction in which A is being pulled by the universe, I just add, for example, some momentum to the spin axis. The axis will change angle, and A will now be pulled in a different direction. So we can simulate a transfer of physical momentum to a particle simply by changing the north-south axis. The radial hypersphere expansion does the rest. Now, photons do not have a mass point state. They have only a wave state. and so they have no means to travel the radial expansion axis as do particles. Instead, they travel horizontally, but this also means that they're traveling at the speed of light in both hypersphere and 3D coordinates. And here, A emits a photon. B is traveling towards A. The period, time required for a particle to emit and then to absorb a photon is proportional to the wavelength, and so it will take B less time to absorb that photon than if B was parallel or moving away from A. This gives us the Doppler shift. But it also means that as the photons only move laterally across the hypersphere and not with the radial expansion of the hypersphere, A, B, and C will not be able to measure the distance from the origin. Instead, they will measure the relative distance across 3D space because they're using the electromagnetic spectrum to do this measuring. And so A, B, and C will see or observe 3D space coordinates. They will not be able to measure directly the universe expansion, the hypersphere universe expansion. This is not the same as 3D space expansion, although 3D space expansion derives from the hypersphere expansion. We can see this in here. We have an object, a satellite B, orbiting planet A. Now, normally we see B, the satellite, orbiting in a circular orbit around planet A. But as B is orbiting A is moving along the timeline axis at the speed of light. And so when we unfold our cylindrical diagram, we find that in a circular axis, in the circular orbit, B is orbiting A at the speed of light. Also, in the cylindrical axis, the timeline axis, B is orbiting A at the speed of light. But people in A will observe B as following a standard gravitational orbit, the gravitational orbit period. The reason for this is that B goes in these steps, triangular steps. So up the axis, the timeline axis, which we don't see. Then across 3D space we see that, and then this we don't see, and so on. And so the end result is that although B is traveling at the speed of light continuously, we only see the circular axis. We do not include the timeline axis. However, in time dilation, we find that TD is the period of orbit including time dilation, and TG here would be the gravitational orbit in classical sense. So we only notice this occurring because of time dilation.